So we welcome Xiao Wei from the Institute of Software, Chinese Academy of Science. We will talk about hybrid and parallel algorithms for SAT and MILP. Thanks, Xiao Wei.
Thank you for the introduction, and I would like to thank Thomas for inviting me to be here to present our work on SAT solving and MILP solving. And it's my honor to be the first time to talk with this community. We have a conference and a CP conference, and with people there talk about constraint solving, and we need interesting benchmarks, which can come from this community, I think. My talk here today is to introduce two recent work about SAT and MILP, hybrid and parallel algorithms. Okay, so I try to explain some basic principles in SAT and MILP solving. So we start from the brief introduction. For symmetric-key cryptanalysis, we usually have constraint solvers like SAT, MILP, and also SMT and CP. And I would also like to mention a special subcase of MILP called pseudo pooling optimization. This special case cares about the variables that have the domain 1 and 0. So as I know, this can happen in symmetric-key cryptanalysis. So maybe we don't, maybe mixed integer linear programming is too, in my viewpoint, is too large for the task here, especially this mixed. Actually, we are dealing with integer variables. So actually just integer linear programming. And more specifically, if we were dealing with 0 and 1, that's PBO problem. So, and the SAT problem cares about the satisfiability of a Boolean formula. And a basic concept is the clause. As we can see, a clause is a disjunction of literals, and a literal be a variable or its negation. And in SAT solver, at least for now, the popular format, the input format is CNF, conjunctive normal form, as the example shown here. So SAT solver try to find a solution or prove that there is no solution to such a formula. Then there are two popular methods for solving SAT. One is called conflict-driven cross-learning. Usually we name it CDCL, and the other is stochastic local search. And roughly speaking, we can say that CDCL is a complete method, as eventually you will prove there is a solution or not, given sufficient time, but the time may be very long. And local search is incomplete because it can only use to find a solution, but cannot be used to prove unsatisfiability. Modern SAT solvers in industries are based on CDCL. And currently, as I will introduce later, actually the current version of the CDCL solver combined local search inside it. So that's the topic I would like to speak later, the hybrid solver. And here is a short history of solvers from my own viewpoint. I would divide the history into 3 stages. In the early stage, from 1960 to 1990, we know there are 2 classic algorithms called DP and DPLL. Actually, DP is based on resolution. And very quickly, the authors find that DP has the issue of exponential memory. So they turn their attention to backtracking-based algorithm, the DPLL algorithm. And after 1990, this direction come into a boom in 20 years. The local search is first time introduced to soft set in 1991 and 1992. And then the DPLL algorithm is involved into CDCL, which is the main popular method today. And there are several famous CDCL solvers such as G-Chav miniset, glucose, and crypto miniset. I suppose crypto miniset is maybe famous in this community because its name has crypt here. And by the way, the original author, Metasus of crypto miniset, we stayed together for about 10 days in Beijing, and we developed a late version of crypto miniset in GitHub. And then after 2010 to today, we enter into a modern time. We have some modern local search because previously local search solvers, they focus on solving random instances, but after 2010, people doing local search consider this is not a good idea, and they turn their attention to focus more on the structure instances. And finally, after several years efforts, they can be competitive with CDCL on solving some structure instances, particularly from the mathematical problems. And so this is also a turning point and possibility that the late hybrid solvers can be built, because now these two methods can be both effective and complementary on solving industry instances. And as for CDCL, a main idea is to propose advanced cross management, because during the process, CDCL solvers learn more and more crosses. And so if the instance is very difficult, then you will learn much more than expected number of crosses in the memory. So that will be a failure. So we need to remove some learned crosses out. And that is the idea in 2009 in glucose. And not much more interesting idea in the sequential solver of CDCL since then. So people turn their attention to the engineering practice, and two typical solvers are KDKL and KeySet. Armin Beer developed these two solvers, and advanced ideas are not from the algorithm viewpoints, but from engineering viewpoints and practices. And then in 2020, we have hybridizing CDCL and local search together. And this is the work I will introduce later. And recent years, more focus are developed on efficient parallel solving. Okay, now we have an overview of the CDCL algorithm. Roughly speaking, there are two parts of CDCL solver. There is a decision part. In the decision part, in each step, we need to pick a variable to branch the original formula into two sub-formula. But actually, before that, we do some unit propagation, which can assign the variables according to inference rather than heuristics. So this is the decision part. And the analyze part concerns about when we're meeting a conflict in the backtracking tree, what the algorithm does. So it will analyze why this conflict happened. And from this failure, what can we learn from this failure? Usually we will learn a lemma, and this lemma can be represented by a cross. So this is very nature that set solver can do the jumping instead of backtracking, because we have learned the reason of the failure. So then we can consider this reason, and we can just skip those variables not related to this reason. So we can back jump, not just backtrack. And this closed learning and back jump is the key ideas in CTCL solvers. And of course, we have more other interesting ideas like closed management and data structure and restarting. But the key idea is conflict-driven closed learning. And actually, the algorithm is named after this idea. So I'm now trying to give a brief introduction to this key idea. Here we have a formula with 6 clauses. And this graph shows how the CTCL solver assign the variable one by one. And the direction means we can see here that we have 2 different types of variables. The first type is the roots. In the roots, there are no inside edge. So that means these variables in this example is variable h, b, y, and a. Means these variables are assigned by heuristics. We design heuristics to give it a value. Here, all the variables are assigned to true. And the other variables, the inside node, means that the value of these variables are not assigned by heuristics. Instead, it is assigned by inference. Take an example. Here, suppose we consider variable d on the bottom. And we can see there is an edge pointed from variable a to variable d. And on the edge, there is a label across 2. So we can check out on the formula. We see the second clause. It is no a or d. Now, this graph indicates that if a is assigned to true, then we can imply that d has to be true. Because when we check the second clause, if a is assigned to true, then no a is falsified. So that clause, if we want to make that clause satisfied, we have only one choice. We have to assign variable d to be true. So that is the inference. And eventually, we can see that this procedure here comes to a conflict. In the end, the last clause becomes an empty clause, a conflict clause. So when we meet a conflict, the analyze part runs, and it will. In the picture, we can see that if we make a cut from the roots to the conflict, that means that we cut the inverse trend so that this conflict can happen. And this cut can have several options. Suppose we make a cut here, then we can learn a lemma that because this cut following this cut, we can find two variables, variable h and variable e. And here variable h is assigned to true and variable e is assigned to true. So we learn a lesson that these 2 variables cannot be assigned to true at the same time. Otherwise, it will lead to the conflict, right? That's what we can tell from this graph. And this graph is called the implication graph because it shows the reasoning trend of the CTCL solver. So if we meet a conflict, we want to learn a lesson from the conflict, then we can make a cut, and then the reason can be learned. And of course, we have various options to make a cut. We can make a cut here or make a cut more closer to the roots. So each cut can correspond to a learned clause. Now in this example, we learned a clause no H or no E, and this clause can be added to the original formula. No changing its satisfiability. And this is the key idea of cross-learning. Now we turn to the second method called local search, and this is much simpler. Given a formula F, then local search organizes all the possible assignments, all the complete assignment. Actually, it organizes the truth table into a supercube, into a network. For example, in the right-hand side, we get a cube. We get 8 points corresponding to 8 possible assignments for 3 variables. And suppose one of them is the solution. What local search does is to start from one point of this cube and jump to another in the next step. So we can see that this method is incomplete. It cannot prove unsatisfiability. But the advantage is that by designing clever heuristics, maybe for large formulas, we can also find a solution quickly. Now I will introduce the first part of our work, hybrid algorithm. This dates back to the challenge of hybrid solvers for sets. And it was proposed in the IIII conference 1997. It's the 7th challenge in the set solving direction. And because we have 2 different types of search algorithm for set, so we are naturally curious about, can we combine their advantage together to develop a hybrid algorithm that can outperform them both? Although we can take it for granted that this is, of course, this happens, but actually it was for almost 30 years to make this come true. And before this work, there are also many works doing the hybrid solvers. Some use local search as the main body solver and try to utilize CDCL in some situation, and some use CDCL as the main body, and some doing the sequential portfolio. But the common limitation is that these solvers take these 2 solvers, and these hybridizing methods take these 2 solvers as the complementary solving ability. So they focus on when to active which one to solve the formula. But if we have a second look, if we take another different viewpoint, we can see local search as a sampler instead of a solver. That means we also use CDCL as the main solver because it's the best in solving industrial instances. But for local search, we can give up the role of solver. We can give up its solving ability. Instead, we can tailor it. We can design it as a sampler. So we use it as a sampler instead of a solver. We use it to gather some information, and this information are used to help CDCL. So whether local search can solve the formula or not is not any more important. What important is what information can you gather that can be used by CDCL. This is the paper published at SET 2021. And the basic framework is we call local search whenever we're meeting promising branches. So roughly speaking, we can see promising branches is a branch deep enough before meeting a conflict. And when we call a local search, if we are very lucky, maybe it can find a solution. But if we are not lucky and the local search fails to find a solution, the time is not wasted, because during this procedure, we use local search to gather information such as the local optimal assignments and the frequency in the unset crosses. And this information are very important for the CDCL branching heuristics. And a short history, a short story I would like to mention is the cooperation between my group and Armin Bier. We work actually independently on the idea of hybridizing methods, but finally we get together and write a journal article, 50 pages. We describe the history that how these two separate lines work and finally converge into a comprehensive work. So now in the latest version of KeySet by Armin Bier, the hybrid idea is there to use local search for KeySet. So how can we use the information to improve CDCL? First, the conflict frequency can be used to improve the branching heuristics, because in CDCL, the branching have a principle. We want to fail fast. We want to find a variable so that we can meet the conflict fast. Then we can cut the branch. So CDCL solvers prefer to find a variable that can cause conflicts faster. And this is the heuristic called VSIDS. So we gather the conflict frequency of variables in local search. Then this frequency means that if a variable is more frequent to happen in unsatisfied clauses, that means this variable may be more likely to cause conflict together with other variables. So this can be enhanced to the basis branches. We can get a normalization, and after that, for each variable, we can increase this variable x with the local search conflict frequency to rewrite the scoring function. And the second information to be utilized is the assignments. In the CDCL, after picking a variable, we need to decide whether to assign it to true or false. Then this is important. Modern local search, modern CDCL solvers use the face-saving heuristic. We propose use local search assignment to do the rephasing resets. After each restart, we can reset the values. We also call phases of the variables with assignments collected by local search. And these assignments collected by local search usually are those good quality ones. For example, the local optimal ones or the best ones it has visited ever. And we have a probability distribution to choose from these local search assignments. And the experiments turn out to be that these references by local search can be better than the random ones or the face-saving ones used in previous CDCL. And so this is the experiments. We apply the idea to 4 CDCL set solvers, including glucose maple, KeySet, and CCNI is a local search solver. Yeah, all the 4 CDCL solvers can get significant improvements. The green number means the additional solved instances number. So we can see a large portion of the instances can be solved after we applying this hybrid methods. And that leading to the winner solver in the SAT competition 2020. And actually, since then to now, in every SAT competition, the main track winner are based on this idea. including the key set or KDKL. And we also have a very interesting observation that on the right side table, we can find a considerable portion of instances that originally can't be solved by either CTCL or local search, but by combining them together, they can be solved. So that means the performance improvements does not simply come from the complementary ability, but actually that these informations have essential help here. Okay, now I will introduce the parallelized solving, and this is for both SAT and MILP. We have two methods for parallelized solving in constraint solving. The first one is based on partition. We divide the search space. Actually, we divide the original problem into sub-problems and solve them separately. For example, this partition tree corresponds to a partitioning algorithm for SAT solving. And a typical method is called cube and conquer. Actually, we can just consider it as a partition algorithm. So the key here is how do we choose the variable to partition the formula? And a popular measurement is we choose the variable to partition the formula so that we can lead to the largest reduction of the formula. Because if we fix the assignment of a variable of an important variable for an extreme case, if there is a backdoor variable, that means that if we fix its value, then many other variables' value can be inferred. So the formula can be reduced to a large extent. And we like to, and we need to find out such important variables for partition. And that is the focus of partitioning algorithm. And also, for this method, we use incremental SAT solver because we are solving many similar instances here. The two subformulas and the parent formulas, the major part of them are the same. They just have a small portion of differences. So we don't need to solve them from the scratch. We can use incremental solver. That means that we can use the experience and learned courses and some other information from previous solving procedure. The second method of parallelized solving is called portfolio. The basic idea is that we can parallelly run different SAT solver at the same time, right? Then the best one is picked. Whenever a solver returns the result, that is the farthest one. So this is a very simple idea. And when we say different SAT solver, it could be one solver with different configurations, because we know currently modern SAT solver has many parameters and many options for one function. So if we can open up the code, we have many options to config its parameter and strategies. Now the key here is we need to design a complementary solver configuration space. So that we can use the complementaries here. And later we find out there is a much slighter and easier way to do the portfolio. That comes from the role of branching heuristic. Because in CTCL, we are actually working on a backtracking tree, right? So the branching order is very essential for this tree. Now, since we know this, we can suppose that if we change the order, the performance of the solver might change considerably. And we did the experiments, and that confirms our conjecture. So this is tested on a benchmark from the SAT competition, and we randomized the initial branching order and it can the time variance can goes down to 0.125 or goes up to 32 times up speed up. That is the runtime distribution. So the simple idea is that for the SAM solver, for each thread, we simply use different orders for the branching, for the initial branching, and that helps a lot. But that is not enough for the portfolio. What makes portfolio critical is the idea of cross-sharing. Why cross-sharing? Because we execute multiple solvers work independently at the same time will cause redundant works because they are the same search space. They are solving the same formula. So maybe the same part has been visited by this solver, but the other solvers, they don't know. So they will search it again. So by share the learn clauses, we can avoid this redundant work because we have introduced that the learn clause presents the lessons learned from the conflict. So these lessons can be shared so that every solver can assess this clause and these clauses. So every set solver also contribute to this clause database and also get access to this database to find out some experience. And this can accelerate the portfolio's performance. And by combining that together, we can we designed a parallel set solver called PRS, and that is the winner of parallel checks in set competition 2020 and 2022 and 23, and also similar idea in 24. Okay, the last one for MILP, we designed a partitioning framework. And this is the whole picture of the framework. We maintain a task partitioning tree. In this tree, we distinguish the 3 different cases for the nodes. We have a running nodes, means this sub problem are being solved. We have closed nodes, that means this sub problem has been solved. And we have some nodes resting, waiting for other results. And the key ideas here include the first, we have to predict which subtask is most difficult, or which parts of the search space is more challenging. And we need to find out these challenging parts to further partition them into smaller problems. And also we need to, after we identify the hard problem, we need to find a variable to partition this problem. So we use the reinverse learning here to find out the correct, nearly correct variable. And also we have the task propagation. The results can be propagated. And we have other techniques here I will not mention in the detail. So finally, we established a new records for 21 challenging MILP instances on the MIP-lib benchmark. This benchmark is a standard benchmark in the MILP solving, and like solvers like Groovy or Skip or OR tools, they whenever we design a new solver, we will test the benchmark to see whether we can establish new results, new upper bounds. And also we close an open instance to the optimality. Okay, finally, I would like to mention that what can be done in constraint solving for cryptanalysis. I suppose that the best one is to design a specific constraint solver. Because we can explore the future. For general solver, we actually every solver are tuned with respect to some benchmarks. If we are not fixed some benchmarks, these general solvers are likely tuned according to the competition benchmarks, because that's what we can find as standard benchmarks. But that those benchmarks, they have different structure from the benchmarks from this community. So actually, we are working on the wrong direction. We have the wrong goal, right? So first, we have to set up the correct goal. We can know we can collect the information such as what are the measure operations, and are there some variables more important than others? These are very useful if we know some variables are more important or more sensible to the performance, then these variables can be branched earlier. And also we can configure the solver. We can tune the parameters, and we can choose the good combination of the strategies. And also a recent very interesting idea is to use LLM for optimize the solver by rewriting the codes. And we have designed an auto set solver that developed by LLM, and we put it on GitHub, and the paper was on arXiv. And this solver is very interesting because we start up with just several hundred codes of C++. And this is a very simple and basic version. But by putting a large model to modify the codes, about 50 iteration, we can get a version that very close to the state of the art. And for some benchmark, it even outperforms the state of the art. So I think this is very interesting. We don't need to be an expert, but we need to know some basic knowledge of the solver, and we can cooperate with the large model. And the final and the second direction, I suppose the sequential solver makes some bottleneck, makes some ceiling effect nowadays, because we have worked on it almost a half century or more. So it is very challenging to improve the sequential solver. But the parallel or even distributed parallel or distributed solving is far from satisfactory, and has much space to be improved. So we trying to find a maybe scaling method. So we can consider the deep learning method, right? When the computing resource is limited, it actually don't have that significant performance. But if we can find a somehow similar to scaling law, then we suppose we are given 10,000 cores to compute one challenging problem. So what can we do? Now this is still a challenge and open question. But I think if we can find a way to do that, then we can find engineering way to tackle the difficult problems. So finally, the selection, how to improve the power of solvers for symmetric key crypto analysis. I suppose that first we can make our benchmarks in this community available to the solver communities. For example, we can submit the benchmarks to SAT, BBO, or SMT competitions. This is very welcomed. And we can make more benchmarks available. Maybe we are also making this possible to maintain a library that we can maintain these benchmarks so that more solver designers can see these benchmarks. That's the goal for them. And we need to bring people from two communities together to sit together to find out the difficulty. And I also encourage you to go to the constraint solving community to introduce the problems from this community. Okay, and welcome to visit us at Beijing. And this is the website. Thank you for your attention.
Thank you so much for the talk. Any question?
Yeah, we have some experience like if we know some spectral structure, for example, we know there are some XOR chain. If we know there is some XOR chain that are transformed into CNF formulas, but they actually originally they are XOR chain. Then there are special methods for this structure. So that's for special structure. And also we will care about the density of the formula. Sparse and dense, that's different. Usually sparse is easier, and we can find some particular way to solve the sparse formula. And we also care about the variables importance. Are they equally important, or if some variables are more important? Yeah.
So actually, with my colleagues, we often thought that with our tools, we can generate all the benchmarks that you want, because we can for all the ciphers we can generate the corresponding SAT problem to find the differential trace for different rounds. So it's good to know that there are competitions. Then maybe we'll try to submit. Yeah. Then one final question. As far as I know, SAT solvers, or in general solvers, they never really exploited the GPUs. Maybe these techniques that you talked about finally will be able to have some step forwards.
Well, actually, there are some attempts on using GPU for SAT solver, but the results are not good, because the SAT solver we still haven't found a way to transform the SAT solver into a manner that GPU suitable. It has complex control flow, so that is bad for GPU. We need to find like a unified way for computation, but it is hard for SAT. Yeah, that's too much communication and too much waiting time, because the controlling flow is too complex, like backtracking some. Yeah. Okay.
Thank you so much again. Yes, sorry. You can ask it offline.